So we're studying the planet Earth. We ended last time talking about differentiation. And so that means the interior of the Earth is going to be different. The interior is going to be different from the outer portions. Well, so we want to actually be able to study the interior of the Earth. And that turns out to be very difficult because, for example, the surface, we just walk around the surface. We can look and see what the surface is like. You can pick up a rock and analyze it. What about the rocks on the inside? You can drill a hole, or start with a shovel, dig a hole, get rocks, but you only get a few feet below the surface. You can drill for a couple miles below the surface, and that's very difficult to get that deep and get some rocks there, but it takes like 4,000 miles to get to the core. We don't have any way of drilling that deep. Just a couple miles is pushing it. And so to find out what's on the inside of the Earth, we have to do something else. Radar doesn't pass more than a few feet into the surface of the Earth. In fact, that turns out not to be very effective. X-rays won't pass to the Earth. So how do we do it? Well, actually, we use sound waves. Something very similar to sonar will pass through the Earth. The bigger the sound, the bigger the farther it goes. So this is actually one of the ways we do this. In fact, that's what geologists do if they want to figure out where's a good place to drill for oil or gas, rather than just randomly spending a few tens of millions of dollars to drill. What they do is they have to figure out what's down there first, where it's likely to be something, and so they do it using sound waves. One way of doing it is they got these trucks that will actually thump on the ground. They actually call them thumper trucks, and they'll thump on the ground, and sound waves will pass into the Earth, bounce off of different layers, come back up. If you want to go deeper than that, you need a bigger sound than the thumper trucks, and so they use something like dynamite, set off an explosion. That passes deep into the Earth, comes back up. We want something louder than that passes greater distances. Nuclear weapons do that. So that's how, for example, we're able to monitor who is testing nuclear weapons, because the seismic waves, the sound waves they produce, actually pass great distances to the Earth. And so if North Korea, for example, sets off a nuke, everybody nearby with seismographs sees the ground shaking, and they know that they did that. And they can work backwards to calculate how big of an explosion it was. And so this is what we do, but we need even louder than a nuke to pass all the way through the Earth. So what's louder than that? Well, earthquakes. They produce enormous seismic disturbances, and they'll pass all the way through Earth. Now, there's two different types of waves. We have what we call longitudinal waves. In longitudinal waves, things are bouncing back and forth and traveling in the direction they're bouncing. For transverse waves, they're bouncing back and forth this way, but they're traveling that way, so that makes them look a little bit different. Mathematically, they're described in a very similar fashion, and so we talk about them pretty much as the same kind of object, but transverse waves and longitudinal waves. Most of what you think of as sound waves are going to be longitudinal waves. Well, in a seismograph, when the ground shakes, you actually make both of these kind of waves. The ground moves back and forth and up and down, and the seismic waves travel, and they actually travel different speeds through the ground. And so a seismograph would suddenly get a jarring and second jarring, so that would be from an earthquake. The first jarring we call P waves, second one S, because primary, secondary. The P waves are these longitudinal waves, and the S waves are the transverse waves. And so since they travel different speeds, if you measure the time shift between those two peaks, you can use that to figure out how far away the earthquake was. And so if you have different seismographs that both measure the same earthquake, you can triangulate on exactly where a fault ruptured and exactly where the earthquake originated. Not just the position, but the depth at which it happened. And this turns out to be very useful for figuring things out. It's also interesting that P waves and S waves travel differently through different kinds of material. In particular, P waves travel through almost anything. S waves do not travel through liquids. So if you have a magma pocket underground, the S waves will not travel through that, but the P waves will, magma being molten rock. Well, as you get an earthquake and these waves travel through, they bend as they travel through. This refraction that occurs, very similar to the way lenses refract light, has to do with differing speeds at which the light travels through the glass. The rocks, again, the density of the rock changes the speed. And so as these things go through, then what happens is they will bend. And they'll bounce off of different layers of different densities, but when they reach the core, an interesting thing happens. They bend, indicating the core is very much denser, but they also only the P waves go through, meaning no S waves, meaning the outer part of the core is liquid. The inner part turns out to be solid because we can see that the waves bounce off of that. And so this turns out to be a way of monitoring the interior of the Earth. In fact, this is the only way we have of finding the interior of the Earth is using these seismic waves that go through there. Interesting enough, because of the way they bend, there are these what we call shadow zones out here. The shadow zones are places where none of the seismic waves go through. Okay, so so they bend around, so you don't hear the earthquake there. If a giant asteroid were coming to Earth, it was going to devastate everybody. You'd have some astronomers, if it's going to be a huge asteroid, it's going to kill everybody. Then you'd have some astronomers that'd be like, congregated right under the impact to get the best view, and some congregating in the shadow zones, where you'd actually live for a few minutes longer. So this is kind of a graphic of the basic structure of the Earth. We have the crust on the outside, we got the mantle, we got the outer core, we got the inner core. So that's the basic